Okay, I'm going to show you how to do some math using dimensional analysis. And this is awesome. I really wish I'd known how to do this in university. So the key parts are it uses ratios. There's no formulas to remember. There's less chance of making multiple rounding errors. And there's less chance of losing marks for missing units. So it's pretty much a win-win. A ratio, what's a ratio? A ratio is a relationship that's written as a fraction. So, like there's 2 hydrogen atoms in 1 molecule of water. And we can flip that and write it the other way. 1 molecule of water contains 2 hydrogen atoms. So we're going to be doing this. We're going to be taking ratios of relationships and flipping them as we need to. So the relationship didn't change here. There's 2 hydrogens in every 1 molecule, or 1 molecule contains 2 hydrogen atoms. The relationship is the same. It's just flipped on upside down. We want to make 2,000 cookies. We know that half a pound of butter makes 50 cookies. How many pounds of butter do we need? So basically what you're going to do is set this up as a ratio. You can do this math in your head. 2,000 cookies, 50 cookies, times half a pound of butter tells you how many pounds of butter you need. So you can do that. But if I said, show me, write it down, would you be able to? So we use ratios here. There's a relationship between the pounds of butter and the number of cookies. So we know that half a pound of butter makes 50 cookies. And we know we have to make 2,000 cookies. So when you use dimensional analysis, you use these ratios. This is a ratio right here. Shows the relationship between butter and cookies. And we use multiplication. So the only math that we use when we set up our ratios is multiplication. And then when we actually do the math, we do multiplication and division. So I'm going to multiply this by the number of cookies, because whatever's on the bottom here needs to get canceled so that my unit is just butter, pounds of butter. So if this is cookies, I have another number that has cookies in it as a unit. You always have to write in your units. So cookies are going to cancel. And so what happens is you multiply everything on the top. So 1/2 times 2,000. And you divide by anything on the bottom. So 1/2 times 2,000 divided by 50 is 1,000 divided by 50, and that's 20. So I need 20 pounds of butter. Okay, here's another example. If you can spend 1,000 pennies a second, and you have a mole's worth of pennies, how long in years will it take to spend the mole of pennies? So you've got to set up some ratios here. We've got pennies per second. We want years, so we need to get some ratios in here. Well, we know there's 60 seconds in a minute. There's 60 minutes in an hour. There's 24 hours in a day. And there's 365 days in a year. So our year is what we're looking for. We want to find years. So we're going to start with a ratio that has years in it. So we're going to use this one. We're going to flip it over though, because we want the unit in our final answer to be on top. So 1 year over 365 days. That ratio is used. Now, the next ratio has to have days in it, and days has to be on top. So 1 day contains 24 hours. That unit's gone. That ratio's gone. Okay, so days are canceled. Now we've got to get rid of hours, because right now we've got years per hour. We want to get rid of hours, so 1 hour contains 60 minutes. Hours cancel. Now we want to get rid of minutes. 60 seconds. Our minutes cancel. So we'll just use those two. Now, we need to get rid of seconds. And we have this ratio over here. So, 1 second goes on top, 1,000 pennies goes on the bottom. And then we have a mole of pennies. So pennies cancel. So setting up your ratios, you set them up as a multiplication. So then what you do is you multiply every number on the top and you divide it by every number on the bottom, or you multiply every number on the top and divide by, in brackets, the sum of these numbers. You have to put it in brackets though, if you're going to do it that way. So usually what I do is I take the top numbers, multiply them, then divide each number on the bottom. But the result is, so that is a long time. You will not be able to spend a mole of pennies if you're spending at 1,000 pennies a second in your lifetime, or your grandchild's lifetime, or your grandchild's lifetime. Okay, so we did a question earlier. What is the number of atoms in half a mole of iron? So we're looking for the number of atoms in half a mole of iron. So we know 2 sets of ratios already. We know Avogadro's number, and we know molar masses. So these are ratios that we already know. Okay, so I used to go from information that I had to my answer. But one of my former students, I think it was Omar Hassan, who's smart, he now works at Google, he started doing it backwards. And it actually made more sense to me after that. So I started doing it that way. We want to know the number of atoms. So you start with a ratio that has atoms in it, and the atoms have to be on the top. So Avogadro's number, the particles, because it's the element iron, the particles are atoms. So 6.02 times 10 to the 23 atoms for every 1 mole. So that's Avogadro's number. The next piece of information, whether it's a number or another ratio, has to have moles in it, because we want just atoms of iron. So we want to multiply it by something that has moles in it. So we're going to multiply this by 0.50 mol, mole. So our moles cancel, and we're left with 3.0 times 10 to the 23rd atoms of iron. So we round that off to 2 sig figs, because 2 sig figs in 0.50 moles of Fe. Okay, how many hydrogen atoms in 4.0 moles of water? So we're looking for hydrogen atoms. We know that there's 2 hydrogen atoms in 1 molecule of water. We also know that there's if the particles for Avogadro's number, the substance we're talking about is water, so the particles in Avogadro's number is molecules, because that's a covalent compound. And we know we have 4.0 moles. So, when we start this question, we're going to start with the ratio, or the value, containing the unit that we want. We want hydrogen atoms, so we're going to start with 2 hydrogen atoms for 1 molecule of water. The next ratio has to have molecules of water in it, and Avogadro's number does. So molecules of water cancel. Now we need to get rid of moles, so we have 4.0 moles. Now our moles cancel. So each time you do this, you are only writing them down as times. So then you do your math. So we've got 2 times 6.02 times 10 to the 23rd times 4 divided by 1 divided by 1. So there's 4.8 times 10 to the 24. That's a 4 hydrogen atoms in 4 moles of water. Okay, what is the mass in grams for 25 atoms of tin? We did this question already. We know that the molar mass is 118.27 grams per mole. We know we're talking about tin, so it's an element. So Avogadro's number is atoms per mole. So these 2 ratios, Avogadro's number and molar mass, are readily available to us. So we've got 25 atoms, but we want grams, mass in grams. So the first number or value that we need to use has to have grams in it, and grams has to be on top. So we're going to use the molar mass first. So there we go, 1 mole multiplied. Now, use that, can't use it again once you've used it. The next ratio has to have moles in it, and we want moles on top. So Avogadro's number has it. So Avogadro's number is flipped over or inverse. So moles cancel. Now I need to get rid of atoms though, but I know I've got 25 atoms. So now I'm done because I have only 1 unit left, and that's grams. You have to put in your units on these questions. So the mass is 4.9115 times 10 to the negative 21 grams. Now I used 5 sig figs because there were 5 sig figs in my molar mass. 25 atoms, that's an infinite number of sig figs, and usually known quantities or conversion factors are given an infinite number of sig figs too. So I'm going to go with molar mass. So there's your answer. The mass of 25 atoms of tin is 4.9115 times 10 to the negative 21 grams. Okay, next question. How many oxygen atoms are there in 125 grams of glucose? All right, so some important information here is that we have glucose. So if it's not given to you, that's something you can look up. So it's C6H12O6. So the molar mass, once you calculate it, is 180.18 grams per mole. The substance we're talking about, glucose, is a covalently bonded molecule. So Avogadro's number is in molecules. So how many oxygen atoms are there? So oxygen atoms is the unit that we want. And there happens to be 6 oxygen atoms in every 1 molecule of glucose. So we're going to start with that ratio because oxygen atoms are on top. So 6 oxygen atoms per 1 molecule of glucose. So that gets rid of that ratio. Now I've got to get rid of molecules. So we can use Avogadro's number. So molecules has to go on top so that it cancels from the first ratio. Molecule per 1 mole. These cancel, and then we want moles to cancel. We don't have the number of moles, but I do know 1 mole has a mass of 180.18 grams. Our moles canceled. Need to get rid of grams, and I have 125 grams. So grams cancel. So now I'm done. I've run out of units to cancel. So in your calculator, 6 times Avogadro's number times 125 divided by 180.18, and that gives you 2.51 times 10 to the 24 oxygen atoms. So there's 2.5 times 10 to the 24 oxygen atoms in 125 grams of glucose. 3 sig figs, because there were 3 sig figs in our mass. Try doing practice problems using dimensional analysis. It's going to save so much of your time when you get to things like limiting excess reagents.